Okay guys, in this chapter we're going to introduce AC circuits or alternating current circuits, and before we do that we want to do an introduction to sinusoids and sinusoidal functions, as well as discuss complex numbers, which will lead us into the discussion of phasors, and then from there we can talk about frequency domain analysis, and then relate that to resistors, capacitors, and inductors, and using frequency domain analysis for that. And then we'll lead us into the concept of impedance and admittance with regards to these elements, and then which again will lead us into the next chapter of doing Kirchhoff's voltage law and Kirchhoff's current law with regards to these frequency domain analyses. Okay, so let's go ahead and start with AC, or alternating current, or I'll use it interchangeably with sinusoids or sinusoidal functions. Okay, the reason why, so thus far we've been talking about DC sources, DC voltage source and DC current source. Now we're going to talk about AC, and again that stands for alternating current, and and mainly sinusoidal current. And as you see here, this current is going to be sinusoidal in this function in a way that it's going to be changing between positive and negative values. Okay, and we'll see that this doesn't necessarily have to be current, and in this figure here it's actually voltage, so the source can be a current source or it could be a voltage source. And the nice thing about sinusoidals functions is they have a lot of nice characteristics from a mathematical perspective, as well as natural phenomenon that will make the mathematical equations easier to deal with. Okay, so let's go ahead and define a sinusoidal voltage. Okay, so let's define V of t as Vm sine omega t, where Vm is going to be our amplitude, and this, most of it should be review, but just in case I'll go through it step by step. Our omega is going to be our angular frequency, and this is going to be in radians per second. Okay, and then our omega t here just together is going to be the argument we're going to put into the sinusoid. Okay, and we'll see why this is important in a second here. So this is going to be our standard voltage source using AC or sinusoidal voltage, and then we'll see we're going to add a phase shift in here. We can change the amplitudes, and this is the basis of what we're going to be dealing with. Okay, and if we look at the figure down here, if we look at the time domain, this is the time domain versus the frequency domain, if you will. You'll see that every t seconds, or every t is a period. So we have, this is our period here, and this is important because we're going to call this capital T from here to here. This is our t. It's going to be our period of the sinusoid. Okay, so then we can look at t here. We can look at t here, and then 2 pi here. So let me change the colors. So if I say t here and 2 pi here, we can say our omega t capital T is going to equal to 2 pi. Okay, and that's important because then we can arrange this and say our period is equal to 2 pi over omega, or our angular frequency. Okay. And one thing with this is we want to, it is a periodic function, so if we shift it, we should also see the shift in regards to t here. And you see that it repeats every t seconds, so every t seconds, or every t here, it's going to repeat. Here 2 pi, 4 pi, it's going to repeat. So we can actually derive this relationship here. So if there is v of little t plus our period is going to equal to v of t here, because the value here is going to be the same as the value here. So the value of our voltage at this point, for instance, is going to be 0. If you add another period, it's going to be 0. If you look at the time domain, here it's 0. Again, here it's 0, and it doesn't have to be at 0. You can start up here at Vm, and then that period goes to Vm. The amplitude is going to be the same here. Same thing here. Up here, we look at the value every time it repeats. So that's what this equation, this relationship is telling us, that depending on the shift or the seconds with regards to the period, those values, in this case voltage, is going to be the same. Okay, so that's just something to keep in mind here. So I'll go ahead and highlight that in blue as well. So these are some properties of our sinusoidal functions. Okay, so we defined, let me go ahead and write this down, our t as our period. Okay, and then we can take the reciprocal of that and call that our frequency. Again, this should be reviewed, but if we take f is 1 over our period, this is going to be our frequency. Some standard definitions. Okay, so we've defined a very standard sinusoidal voltage function. We've got our frequency, and the frequency in this case is going to be cycles per second. It's not going to be radians in this situation. So we can define our frequency here in hertz. So our omega, we said, was angular frequency, and now our f is going to be in hertz, or Hz. Okay, well, as opposed to our omega is going to be our angular frequency. Okay, and we can go back and forth between our f and our omega through this relationship here. So our omega is going to equal to 2 pi f. Okay, so we can go back and forth between our frequency in hertz and our angular frequency through this relationship. Okay, so cycles per second are hertz, or our angular frequency is radians per second. Okay, the other thing we note with regards to sinusoidal functions is we can, so let me go ahead and rewrite this here. There's going to be phase shifts that we want to deal with. Okay, so we can come up with a more general expression. So let me scroll up here. Come up with a more general expression. I can say v of t is equal to, or Vm, our amplitude, sine of omega t plus phi, which is going to be our phase. Okay, so in this case, this is going to be our phase, and that's when we're looking at phase shifts. And this phase can be in radians or it could be in degrees. Okay, so this could be radians or degrees, depending on how we're approaching the problem. Okay. So if we look at this figure here to the left, we have one voltage source, V1 is equal to Vm sine omega t, and the second one, V2, is equal to Vm sine omega t plus phi, and you'll see that they are of same amplitude. So we got the same amplitude, Vm, okay, but now there's a phase shift, so there's going to be this phase shift of phi. In this phase shift, you look for V2, it starts sooner than V1, so it starts before it. Okay, so we say, with regards to terminology, V2 starts first in time, so that we say V2 leads V1, and it's going to lead it by phi, this angle. Or you can say the other way, you can say V1 lags V2 by phi or phi, however you want to pronounce that. Okay. Okay. So in general, if you come back to this equation here, if we have two sinusoidals and you see that this angle or this phase is not zero, then we say the signals are out of phase. Okay, so when phi does not equal 0, okay, V1 and V2 are out of phase, or there's a phase shift. Okay, so again, some standard definitions to just consider as we move forward with sinusoids, and we look at the relationships between the two when we're doing signal analyses. If they are in phase, so if phi equals 0 or phi equals 0, then they are in phase, and then that means, again, if they are in phase, that means the peaks are going to reach the maximum at the same time. So this would be shifted and they'll overlap. Okay, their amplitude doesn't necessarily need to be the same. Okay, the Vm doesn't necessarily need to be the same. So you can have two signals of different amplitudes and still be in phase, as long as that phi is equal to 0. So they'll reach their maximum and minimum at the same time. Okay, so one thing about sinusoids, they can be, as you've noticed here, they can be expressed as both sine and cosine. So they could be, let me just move up here, sine or cosine functions, and it's just a phase shift, right? The difference between sine and cosine, just a phase shift is the difference between them, and then you can convert between the two. So let's come up with some standard definitions here. So sine of omega t plus or minus 180 degrees is just equal to minus sine omega t. Cosine of omega t plus or minus 180 degrees is just minus cosine omega t. Again, you can convert between these back and forth. Sine of omega t plus or minus 90 degrees is going to be plus or minus cosine omega t, and then cosine omega t plus or minus 90 degrees is equal to minus plus sine omega t. So these are standard mathematical definitions and relationships of sinusoidal functions. That's good to keep in the back of our mind as we move forward with sinusoidals. Okay. Before we move on to complex numbers, I do want to say that you can actually see these in a graphical approach. Okay, you can look at this in a graphical approach where you look here on the left side, we have the relationship between cosine omega t and sine omega t. Okay, so in this case, in this figure, we have cosine omega t minus 90 degrees is going to give us sine omega t. Okay, so if we start off with a cosine omega t and we go in the negative direction 90 degrees, that's going to give us a sine omega t. Okay, so that's one way of looking at it in a visual fashion. And then the second figure here, part B, what we have is we have a sine. We start at sine omega t and we add plus 180 degrees to it. Okay, that's going to give us a minus sine omega t. Okay, so we start off at plus sine omega t. We're going to go in the positive direction here. Counterclockwise is going to be considered positive, and that's going to give us minus sine omega t. So one thing to note about these graphical approach is that the convention is the y-axis is going to be our sine, in the negative direction are going to be positive sine, and then our x-axis is going to be our cosine, and to the right is going to be positive. So this is how essentially you can look at this relationship between these and these charts, these guys. Okay, so you can go between these two either by memorizing those equations, knowing them mathematically, or looking at the chart. Okay, so let me go ahead and highlight this here. So this is the relationship mathematically, and this is the relationship visually, if you wanted to convert between the different sine and cosines. Again, this will be advantageous as we using this graphical technique and understanding these relationships as we get more into the frequency domain analysis and alternating current or AC circuit analysis. Okay. A couple other things I want to introduce here before we move on to complex numbers and phasors is we can use trigonometric identities as well to look at the graphical approach method. Okay, so let's go down this other figure up here. Let's look at this figure here. Again, we have cosine is on the x-axis, sine is on the y-axis. Okay, and this is something you're probably more familiar with. Okay, so if we look at the relationship, let me give you a generic definition. You can have a cosine omega t plus b sine omega t is going to equal to c cosine omega t minus, we'll say theta in this case. Okay, where we can define c as the square root of a squared plus b squared, and then theta is going to be tangent inverse of b over a. So essentially Pythagorean theorem. All right, so let's look at this example here. These figures on the left, bottom left here, we can add 3 cosine omega t and minus 4 sine omega t. Okay, and we can get the result. So the result is going to be 3 cosine omega t minus 4 sine omega t is going to equal to 5 cosine omega t plus 53.1 degrees. Okay, so we have plus 3 cosine. So this is plus 3 cosine here, and then we got minus 4 sine. So going up is going to be negative here, and it's sine. So minus 4 sine. It's going to give us this amplitude. It's a 3, 4, 5 triangle. So we get 5 here, cosine, 5 cosine 53 degrees. So omega t plus 53.1 degrees, and that's how we get this. Okay, so that's a graphical approach to looking at these trigonometric identities without having to memorize them. I just want to introduce that before we move on to complex numbers. Okay, again, this is a quick introduction to sinusoids because they're the essence of AC, or alternating currents. And we're using sine, but we can easily switch between sine and cosine. It's just a matter of phase shifts, and we can look at them graphically using the identities or using some conversion factors here. Okay, so we'll stop here for this introduction, and then we'll go into complex numbers before we get into phasors.